All right. Hello, everybody, and happy Earth Day. Thank you to everybody near and far for tuning in for this wonderful event. My name is Curtis Dankof. I'm one of the outreach supervisors here at Lowell Observatory. I've been working in the education and outreach department for a little over 4 years. I ended up finding my calling there after I graduated college with a degree in astronomy and physics. And I just love bringing science and astronomy to the public. So I'm so glad to be doing this, sharing this wonderful Earth Day with everybody. Earth Day very much may be my favorite of all the holidays because everybody in the entire world can celebrate it, no matter where you are, when you are, no matter what. It's our holiday as humans. And today I'll actually be joined by several of our Lowell educators, as well as our director, Dr. Jeff Hall, as we all celebrate this wonderful day. And so in honor of the 30th anniversary of the very famous pale blue dot image, the anniversary of that being just last Tuesday of last week, February 14th, I apologize. We're just going to be talking about Earth's place in the solar system and the importance of protecting our home, the one home that we have right here in our solar system. So throughout the stream, feel free to post questions in the YouTube chat. We have several educators and staff standing by to answer those, as well as myself. So I'd love to hear some questions from you. See if you can stump me or anything like that. I really appreciate the questions. So definitely ask away. And let's take a look at that famous image. So we'll head on over to this next slide. The very famous pale blue dot, made famous by Carl Sagan, great Carl Sagan. This picture remains one of the most iconic images in human history, taken by the Voyager 1 spacecraft, which was built back in the 1970s by thousands of men and women who poured their hearts and souls and their educations into this project. And as it was out in the outer reaches of the solar system, almost 4 billion miles from home, it turned around at the request of Carl Sagan and just took a picture of us, of what we call home. And throughout that image, you can see little streaks coming through of different colors. Those are streaks of sunlight reflecting off the camera. And there's a tiny little blue dot just about the size of 1 pixel. Carl Sagan just said something to the likes of, that's home, that's us, that's everything we've ever known and ever really will know. And so we just never really lose sight of our home, no matter how far away we are. If we move on to this next slide, we see that we really are this blue marble, as sometimes Earth is called, just this very blue dot out there in kind of the blackness of space. And as far as we know, it's the only place where life exists, and especially the only place where humans could survive, particularly in the solar system. And so it's our honor and responsibility to take care of our planet, to protect it, preserve it as much as we can. And that allows us to enjoy it, right? To be one with it. And so it's true that no matter where we go, how far from home we ever are, we always want to just feel connected to it. And I think this next picture, this next slide, illustrates that perfectly. It's one of my favorite pictures ever taken by a human, probably my favorite picture ever taken by a human. And it is from Apollo 11. And on Apollo 11, Michael Collins, the astronaut, was on board the command module in orbit around the moon, while Neil Armstrong and Buzz Aldrin were doing their famous moonwalks on the surface. And in this picture, you can actually see the Eagle coming back up, the Eagle being the spacecraft that landed on the moon, coming back up to redock with the Columbia, the command module where Michael Collins was, and head back home. And contained in this picture, Neil Armstrong and Buzz Aldrin aboard the Eagle and Earth. Every single living thing there ever has been contained in that picture, except for one. And that one person is Michael Collins. It's just an amazing picture to me. Always makes me feel a little emotional seeing it. So I always love to share that with anybody I can. And so Earth it's truly unique. It's so special. But by studying it, we can actually learn an incredible amount about other planets and other moons, other regions of our solar system. And so here to talk about exactly that is one of our educators, Melissa Panter, and she'll be talking about how the Earth can be used as an analog for other places in our solar system. Make sure if you have any questions for Melissa, set them up in the chat, and she'd be happy to answer them. So let's go over to Melissa.
Thanks, Curtis. My name is Melissa. I am a public educator at Lowell Observatory, and today we are celebrating my favorite holiday. It's Earth Day! So let's get started looking at our Earth as an analog. Now, us astronomers and scientists, we tend to look more towards things out from our home, so outer space, the universe, our solar system. And what's kind of interesting about this field of study is actually trying to find ways to understand what we're seeing through a telescope or through the pictures we take to find what's really going on out there. Ultimately, we are fortunate enough that our Earth can be used as an analog. The definition of an analog is a person or thing seen as comparable to another. So what we're seeing here on Earth might explain these extreme environments that are happening on other planets. We use analogs here on Earth in comparison to the moon, to Mars, to exoplanets, but we also use them to compare things on our own planet first. Paleontologists actually use our Earth as an analog when comparing our present environments to our ancient environments, trying to figure out what was happening on our planet billions of years ago, using those clues like fossils or rock sediments and comparing them to what we have here on our planet now. That same idea can be used when exploring other planets in our solar system and space. We can use the clues that we're seeing out in our pictures or the images we gather and compare them back to environments here on Earth. Now, we used this idea of our Earth as an analog back when Apollo missions in the 60s were happening. It's one of the most unique times to be exploring outer space because we hadn't really left our own planet. These astronauts, or these trainees, as they were called at the time before they went to the moon, were taken to some of the most beloved landscapes across the world and attempted to practice in geological environments here on Earth what they thought they might encounter once they got to the moon. They went to places like, in this photo right here, Sunset Crater National Monument here in Flagstaff. They also went to places like Meteor Crater, also in Arizona. And they were able to take these environments, whether it's the basalt volcanic rock or it's a huge meteor crater like this, they were able to practice their science. So how their suits held up while picking up rocks, how they could identify different geological rocks and make sure they're picking up different kinds of samples to bring back here to Earth. They also got to test their rovers to see where these tires actually work once they got to the moon on many different environments, or is all of this going to fail? Now, this played a really important role in our astronauts going to the moon because aside from their main task of being the first to walk on the moon and explore it, there was a huge component behind geology, picking up rocks and bringing them back so we can understand the moon more. So they were able to practice the rocks. These astronauts actually did not really care for geology at the time. Only one astronaut out of like 32 was a scientist in geology. The rest really didn't care until they went to the Grand Canyon. There is one astronaut who is quoted, "We've listened to you for 2 weeks in a classroom setting and not understood. And one field trip has shown us the importance and the reasons for all the discussion." So after seeing this crazy geological event that happened at Grand Canyon and researching these rocks and learning about the geology of our own world, these astronauts were actually able to care about the mission of rocks, which really rocks. No pun intended. So we used our own Earth as an analog to go explore the moon. Now humankind has a new exploration in mind, and that is to become frontiers of the planet Mars. The planet Mars is about 122 million miles away. We have sent things like our rover Curiosity that help us understand what's actually happening on this planet. We're able to take these photographs and the samples it collects and revert it and compare it back to Earth, which really crazy to think about. Our rock formations like this right here, you can see that these rocks actually have layers. These are sedimentary rocks. Sedimentary rocks happen layer by layer over time, and we have very similar rocks here on Earth. I even see things like this all the time while hiking in northern Arizona, whether it's the Grand Canyon or in Sedona, Arizona. You can see similar rocks like these right here on Earth. Curiosity has encountered lots of different kinds of sedimentary layers. A lot of them have been gently deposited at the bottom of, say, like a lake. Others are layers that kind of note that maybe there were larger rock structures that could have formed only in a high energy environment, like flowing streams or being windswept, like the hoodoos. These structures are showing us these geological processes that are happening on Mars that we can actually compare them to what's happening or what happened here on Earth. So our Earth is really important in putting together all of these ideas of what's going on or what happened billions of years ago on Mars by just using photos and a rover. Just imagine what we can do once we get actual humans up there taking in more information about what they're seeing and experiencing and comparing it back to home. Now, we have lots of analog missions that NASA likes to send our astronauts on. And an analog mission is where these astronauts are put in extreme environments found here on Earth and test equipment just like we did with the Apollo astronauts, or as we explore new locations like Mars, how can we have our astronauts survive and thrive when going into outer space? I chose this NEMO mission as my favorite. It is the NASA Extreme Environment Mission Operations. NEMO is found near Florida, and it's actually for aquanauts. So our astronauts or our aquanauts will go deep dive into the ocean and then survive in this underwater facility for months at a time to start to kind of really understand what they're going to put their bodies through once they go into outer space. It's also a great extreme environment to practice. So before, we had astronauts for the Apollo missions practicing rocks here in Arizona, where these astronauts are practicing picking up rocks in the depths of the water with all of that pressure all around them and exploring all of that fun stuff. I'll wrap this up with a couple extra thoughts for you to think about. Our planet Earth is very special to us, but it's also very special in terms of understanding what's out in our universe. So on that note, happy Earth Day, everybody. And back to you, Curtis.
All right. So thank you very much, Melissa, for that. And even though we see that Earth can be used as an analog for so many different places in our solar system, it's truly unique at its heart. There's no place quite like it anywhere in the solar system and anywhere else we can find anywhere. So one of our educators, Kathryn Turrentine, will actually be talking to us about some of the things that makes Earth incredibly unique, and giving a few examples of those. And make sure, again, if you have any questions at all, type them up in the chat and we'll be sure to answer them. So let's head on over to Kathryn.
Hello, my name is Kathryn Turrentine. I am a student at Northern Arizona University. I am studying physics and astronomy, and also I am a public educator here at Lowell Observatory. Tonight, I am going to talk about how the Earth is very unique to us, how it's our one and only home. So yeah, our Earth is very unique to us. So if we begin, our Earth is located in the zone called the habitable zone in our solar system. The habitable zone is where a planet orbits around a star, which provides an accurate atmospheric pressure, and also the planetary surface can sustain liquid water. The habitable zone is also nicknamed called the Goldilocks zone, from the children's book, The Three Little Bears. Venus and Mars are located in the habitable zones, but they're on the edge of it. Venus is way too hot for life, and Mars is way too cold for life. Earth meets the perfect criteria for life, so it's just right. Also, our Earth is called the water world too. Over 70% of the Earth's surface is covered in water. The water on our planet exists in the air as water vapor, rivers, lakes. It's in ice caps, glaciers, and in the ground as soil moisture and as in aquifers. If you place all the water in the surface into a sphere, it would be roughly about the size of the western United States. The sphere would be about 860 miles in diameter. Water is very important to life. We need it to survive, especially up here in Flagstaff, Arizona, where we're over 7,000 feet above sea level. So drinking water is very important to us, so we can all stay hydrated. Also, water rarely stays still. The water source from our world is continuously shifting from one location to the other, from one process to another, due to the water cycle. As seen from Melissa's talk, the Earth has a majority different types of landscapes throughout the planet. For example, it has mountains, oceans, forests, canyons, and also deserts. This is another reason why our Earth is very unique to us. In the different landscapes, there are many different species that live in very different ecosystems. Animals that range to the deer in the forest and the emperor penguins in the cold terrain of Antarctica. The tallest mountain on Earth is Mount Everest, which is located in the Himalayas. The biggest ocean is the Pacific Ocean. The picture on the bottom center is the Grand Canyon taken by the ISS, and it's only located about an hour and 15 minutes away from Flagstaff. Next, our Earth is the only planet with an atmosphere in our solar system that can support life. The layers of gases that compress not just the air we breathe, it also protects us from heat and radiation bursts from the UV lights coming in from the sun. It warms the Earth throughout the day and cools it in the evening. The atmosphere is about 300 miles thick. with most of it being close to the surface. With altitude, the atmospheric pressure reduces. For example, at sea level, the air density is about 1,400 pounds per square inch. That is roughly having a large cat sitting on every square inch of you. The air density at 10,000 feet is about 10 pounds per square inch. So that means there's a lot less oxygen to breathe. For example, Venus does have a thick atmosphere, but if you were on the surface, the atmospheric pressure is about 100 times that if you were on sea level. So that would be about 1,400 pounds per square inch. Just say about having a large moose sitting on you. Also, our atmosphere is made out of 75% of nitrogen, and about 20% of it is just the oxygen that we breathe. This photo, taken from the International Space Station, was taken about 258 miles above the English Channel. It shows the lights of the northern European cities. This light is called light pollution, which Sabrina will talk into further detail. Our Earth has one natural satellite, which is our moon. Our moon is very important to us too, because it helps create the high and low tides in the ocean we see. To end up on this note, this is the famous Earthrise photo from the Apollo 8 mission. It was the first man mission to the moon. It entered the lunar orbit in December of 1968, containing the astronauts of Frank Borman, Jim Lovell, and William Anders. While holding a live stream, Lovell said, "The vast loneliness is inspiring, and it makes you just realize what you have back there on Earth." As we conclude, our Earth is very unique to us. It is our one and only home. Located in the habitable zone, it is full of water so it can sustain life. Also, the Earth has an atmosphere to protect us from the outside elements of space. Thank you so much for listening in, and I will be answering any questions that you have down in the chat. And have a happy Earth Day.
All right, so thank you, Kathryn, for that. Remember, all you viewers out there, if you have any questions at all, especially for Kathryn, put them there in the chat. She should be standing by to answer some of those. And so now we see that Earth is so unique, but just how unique is it? Could there be another Earth out there? And that's one of those big questions that astronomers are trying to answer. And for the first time in human history, we're at a point where we might actually be able to start to answer that. For most of human history, we've always wondered, could there be other life out there? Could there be other places humans could survive amongst the stars? And up until the 1990s, the early 1990s, we had no evidence of any other planets out there beyond our solar system until we found one. And so this first slide that I'm going to bring up is an artist's impression of the first exoplanet ever confirmed. And it was orbiting a pulsar, which is basically the husk of a dead star, a very difficult place for life to try to exist. But this was the first step towards understanding there's more out there, that our solar system maybe isn't completely special. Again, that's one of the big questions we're trying to answer. And so this really started the snowball effect rolling. We started realizing that there are so many more planets out there. This 30 years after the first discovery, we now know thousands of planets orbiting other stars. And we call these planets exoplanets or extrasolar planets. They're planets outside of our solar system. Right? They orbit their own stars. And I'd like to take you through a few of these, of the most potentially likely to have life, or maybe ones that we could visit one day and maybe try to survive on. So we're going to move on to the next slide to really the first Earth-like planet ever discovered. And when I say Earth-like, I really mean it has the potential to maybe be like Earth if a lot of different parameters are met. And this planet is named Kepler 186f. So very fancy name. Maybe one day, if it maybe has life, it'll get some other name. But this was an exoplanet discovered by the Kepler Space Telescope, which we'll talk a little bit about here in just a few minutes. And this is a planet that's believed to be roughly about the same size as our planet Earth, and it orbits in what's called the habitable zone, or the Goldilocks zone, of its star system. And so the Goldilocks zone is the region around that star where it's not too hot, not too cold, but just right, where liquid water could exist on the surface. Again, if certain parameters and certain conditions are met. We see kind of on the top right of this image here that there are multiple planets within this Kepler 186 system. There's there's B, C, D, E, and then F is within that little green zone. That is that habitable zone. So anything within that orbit, within that region, has the chance to maybe have liquid water. And you can compare that on the bottom of the image there to our own solar system, where you see Mercury is well within that, much too hot. Earth is kind of right in the middle of that green band, and Venus is just on the inner band where it's maybe a little bit too hot. I also should mention that the Kepler 186 system is not a star like our own. It's actually a star that's much smaller and a little bit cooler in temperature. And so even though this planet, Kepler 186f, is actually much closer to its host star, it actually would be somewhere potentially around the same temperature as Earth because of that star being smaller. But probably my favorite of all the discovered exoplanets so far is actually on this next slide, and that is Kepler 452b. And this, to me, is probably the most Earth-like, if you will, or the one that has the highest potential to maybe harbor life. And this is the first really mostly Earth-like planet to be discovered around a sun-like star, so a very similar star to our own, being yellow, kind of an average star. And this planet, we believe, has a mass somewhere around 5 times that of Earth, so we would all be a little bit heavier on that planet. It might kind of feel like we're all coming off of the holidays. We've all eaten a little bit too much if you ever land on that planet. But most other things will feel very similar. For instance, it has about a 385-day orbit, so it's going to feel very similar. You're going to have that same length of year. You can celebrate your birthdays as normal. It won't be too weird. Now, what's really incredible about this star system and this planet is that it's actually older than our solar system. Our solar system is believed to be somewhere around 4.5 billion years old. And this star system and planet are believed to be about 6 billion years old. So it's had an extra 1.5 billion years to develop, for life to evolve, and conversely, maybe for life to be hit by asteroids like the dinosaurs. So you never know what could happen on these planets, but just the possibilities are incredible. Now, the one downside about this planet is that it's not nearby. There's not really a great hope of us going there to study it. It's about 1,400 light years away. So that light that we've observed from this star system left it about 1,400 years ago, and we're just seeing it now. And so if we were to travel there, say for instance we hitch a ride on the New Horizons spacecraft, which flew by Pluto back in 2015, it's going 37,000 miles per hour, and it will still take about 27 million years just to get to this star system and planet. So space is big, everybody. There's a reason it's called space. It's very empty. But there are other ways we can hope to kind of study this planet. And so if we move on to the next slide, we can actually see just a comparison of our solar system to the Kepler 452 system and the Kepler 186 system, and kind of shows that the habitable zone or the Goldilocks zone in that green area around each of those stars. What I'd love to point out here is that Venus, Earth, and Mars on the bottom ring there in our solar system are all basically inside the habitable zone. Mars just inside the outer edge, Venus maybe just outside the inner edge, and Earth pretty close to the middle. And so even if you say Mars is in the habitable zone, we know that there really isn't any life on Mars that we can find as of yet. And so when we do find these planets in these habitable zones, we have to be very careful not to just immediately jump to conclusions and say that there's life there. Because as we see with Mars and Venus, sometimes it just doesn't work out. Even if you have the chance to have liquid water on your surface, other things may have gone wrong, causing you not to have that. Okay. And now if we move on to the next slide, we'll actually see that there are a number of star systems that have more planets than just one, right? So, actually, before we get into that, we have a question here from Jim Davies. Let me answer this one real quick. Can we detect magnetic fields around exoplanets? To my knowledge, we cannot. Magnetic fields can actually be difficult to actually even detect around some of our own solar system objects. So from the distances we are at observing, we really won't be able to observe magnetic fields. Now, for those of you watching, why that might be important is that the magnetic field around planets can actually help protect the atmosphere. For instance, our magnetic field around Earth helps shield us from solar wind, solar radiation, and keep our atmosphere really there for us to breathe. There are theories that suggest that Mars may have had a liquid water ocean and rivers and an atmosphere, then lost its magnetic field and everything was stripped away. So magnetic fields are probably very important for life and water for these exoplanets, but as of now, there's no way to detect these around exoplanets. And another question here from Claire Gibson. And by the way, Jim, thank you for the great question. So Claire asks, are we targeting any specific types of stars to look for habitable planets? Wonderful question. So not all stars are created equal. As we saw with the Kepler 186 system, some stars are very small, a little bit cooler than our sun, generally more of a red color. Then we have our sun, which is kind of more of a yellow. And then there are much, much larger stars, which can oftentimes be blue in color, very, very blue and hot. And as it turns out, the larger the star, the shorter lifespan it has. And so with our sun will live for about 10 billion years or so. We're about halfway through that, so no need to worry about that anytime soon. But these larger stars on the high end of stellar mass really are a concern because they don't live long enough for planets to really form, for life to form. They can live for sometimes only about 10 million years before they explode in a violent supernova. So those aren't necessarily the planets we want to target. However, on the other side of that, for small stars, there are some concerns there as well. Small red dwarf stars or M dwarfs are notoriously ornery. They can have very large solar flares that can make life very difficult on the surface. So the more we learn about these stars, the more we learn about these stars, the more we can try to understand what these planets might be. All right. We have another question here. Could the presence of an atmosphere allude to the presence of a magnetic field? Quite possibly, I would say, if there is an atmosphere present, a stable atmosphere, it could mean that there's a magnetic field protecting it. I wouldn't say that's necessarily mutually exclusive, but it seems like a pretty good starter bet to say there's an atmosphere there, it's being protected by something, most likely a magnetic field. Again, what's amazing is the more we study, say, Earth and our magnetic field and our atmosphere, the more we can actually learn about all of these. All right. Jesse Kaufman asks, are exoplanets still being detected by measuring the starlight blips as the planet pass in front of and the wobble of the stars, or what other ways are there to detect them now? So, very good question. There are a number of ways to detect exoplanets. If you want to know a lot more about them, I would look at a video that we posted last week at Meet an Astronomer with Dr. Joe Lama. He's one of our Lowell astronomers and exoplanet expert, if you will. He talks a lot more about that, but I'll go into this question just a little bit here. The transit technique, the starlight blips, if you will, is really the main method of detecting exoplanets. As we're observing a star, we're seeing its starlight, and if a planet is present and passes in between us and that star, you'll see a little dip in the light. We call that a light curve. And based on how deep that little dip is, how long it lasts for, we can start to kind of understand how large that planet may be, how far it is from its star, which we can then start to figure out its orbit. So that's the primary way to discover this. The other way you mentioned there is the wobble of stars. It turns out that stars and planets kind of pull on each other. They have this tug. And so if a planet is present, it will actually start to make the star wobble. It'll start to move a little bit, very small amounts as well. We call this radial velocity. And so we can observe that wobble by taking what's called a spectra, breaking apart light into the rainbow and seeing if it moves towards us. If the star is moving towards us in its wobble, the light that comes from it will actually look a little bit more blue. And if the star is moving away from us, it will look a little bit more red. We call it red shift and blue shift. And we actually have a piece of equipment on the Lowell Discovery Telescope, our largest research telescope, recently installed, called Express, which I'll actually talk about here in just a few minutes. And that will actually be searching for Earth-like planets orbiting sun-like stars. The goal is to observe about a 10 centimeter per second radial velocity. So viewing a star that's moving towards us or away from us at about 10 centimeters per second. It's incredible, the technology. Again, we'll talk more about that in just a couple minutes. So before I get to this next question here from Man in Block, I want to talk just a little bit more about the TRAPPIST system there that we have up on the screen. So the TRAPPIST system is a group of 7 planets that were discovered around this star, TRAPPIST-1, and these planets are all roughly Earth-sized. And we believe that 3 of them, D, E, and F, may actually be within the habitable zone, or that Goldilocks zone. Much like our solar system, where we possibly have 3 planets close to the habitable zone, maybe TRAPPIST-1 is similar in that maybe out of the 3, one of them has the right conditions for liquid water. It's tough to tell. But now to address the question from Man in Block, Man in Block says, we know that the TRAPPIST planets are tidally locked. So in your opinion, do you think that makes it more or less likely that life could exist there? So yeah, wonderful question. For those of you watching, tidal lock, being tidally locked, basically means that the same part of that planet always faces the star. A great example of this is actually our moon. Our moon is tidally locked to Earth. That's why you always see the same face of the moon. No matter where you are, no matter when you're looking up, you never see that far side of the moon. And so if you imagine a planetary system where the planets are most likely tidally locked to the star, it means that half the planet is going to have just all-day sun and half the planet all-day night. And that can create some major problems, of course. Right? It's going to be very hot on one side, very cold on the other. There are some theories that say maybe life could exist right along the edge where it turns from night to day. Maybe it's perpetually sunset or sunrise right there. But there are larger implications at place for things like atmospheric studies. Can atmospheres exist with that type of hot and cold on one side. I'm definitely not, anybody who studies anything in atmospheres or a climatologist or anything, but that may be difficult. But again, as I've said before, the more we can study about Earth and understand our own system, the more we can try to understand these other systems out there. So really, just the more we can learn about Earth, the better we will be. All right, so yeah, fantastic questions there, everybody. So yeah, TRAPPIST-1, awesome system there. So let's move on to the next slide here, where we're going to be talking a little bit about the equipment and instruments that are instrumental, if you will, in discovering exoplanets, trying to find other worlds like Earth. And probably the most famous of these is the Kepler Space Telescope, which was in operation from about 2009 till just a couple years ago in 2018, when it was decommissioned, or the telescope is no longer in operation. But Kepler went up into space, and it focused on one part of the sky, only about the size of your palm at arm's length, just a small chunk of the sky, and it just watched. It just looked for mostly those transits that we talked about earlier, those dips in the light coming from the star. And as it turns out, Kepler found thousands of exoplanets, just absolutely thousands of them. There are even more that are unconfirmed that we hope we can confirm in the future. So Kepler was absolutely instrumental in discovering all these exoplanets for us to study further. But the next generation of telescopes is coming up soon, so let's take a look at that on the next slide. On this new exoplanet studying machine is called TESS. It's a new space telescope, stands for Transiting Exoplanet Survey Satellite, and it's up there in space, and it is not just looking at one single part of the sky, it's actually looking at every part of the sky throughout its 2-year mission, looking for as many exoplanets as possible. And so on the next slide here, you can actually see the coverage that it will basically look at within that 2-year period of its mission. By the way, it did launch back on April 18th, 2018, so 2 years ago and 4 days ago. So happy belated 2-year anniversary to TESS. And so every 27 days, it will move to a slightly different part of the sky. However, there are overlapping regions, which are noted by especially the red in this kind of circle. And what's really a great part of that overlapping area is that it has continuous coverage for 2 years, or at least 1 year, on that zone. And that little red zone there is where the James Webb Space Telescope will be looking continuously, looking for some exoplanets, maybe able to study those, which we'll talk about in a minute there. All right, so let's move on, actually, to the next slide, where we do have a picture of the James Webb Space Telescope. This is the next generation telescope. It's the successor to Hubble, and it is supposed to be launched hopefully next year, and this is the plan right now. The picture on the screen there is of James Webb in a NASA facility where it's being constructed. They've entered into the final test phase. I'm personally very excited about it. But this is a telescope that will be launched up to space beyond the moon. It's going to go way out there into space. And this is the first telescope that might have a chance at studying atmospheres of other exoplanets. Right? So of these faraway planets around other stars, this might be the first telescope to actually figure out what's in their atmosphere, if there is anything, if they even have an atmosphere. And so it'll be looking for signatures of life, biological signatures, like, let's say, for instance, oxygen, right? Molecular oxygen would be huge to find. Nitrogen, right? The things that are in our atmosphere, let's look for those abroad. And here at Lowell, we are actually searching for exoplanets as well. So this next slide has a picture of our 4.3 meter Lowell Discovery Telescope. It's kind of our crown jewel, our best research telescope we own and operate. And it's located about 40 minutes outside of Flagstaff here in a little town called Happy Jack, nice and far away from any city lights, nice and dark. And that telescope has a brand new piece of equipment on it, which is on the next slide here. And it is called EXPRESS, which stands for the Extreme Precision Spectrometer. This is a very large piece of equipment. You don't have really a sense of scale from this picture, but if I was standing next to it, the top part there, the top kind of silver bar, would probably come up to about my shoulder, maybe even my head. So this instrument has its own room at this Lowell Discovery Telescope. The instrument was designed and built by our partners at Yale University for this telescope. And it is actually the world's most precise spectrometer. It is the instrument that will hopefully allow us to find Earth-like planets orbiting sun-like stars. Because again, that's really the goal. We know so much about Earth, we know so much about our sun, so if we can find an Earth-sized planet around a star that's similar to our sun, we'll have an even better chance of understanding that planet and hopefully finding life, or maybe one day ourselves exploring it. All right. Once again, if you would like to learn more about exoplanets in general, or learn more about the ways of discovery, or some of the instruments used abroad and at Lowell to search for these exoplanets, I definitely urge you to check out one of the other videos that we posted last week. It was a live stream with Dr. Joe Balma, our exoplanet expert and Lowell astronomer. Fantastic video, fantastic guy as well. And he can tell you so much more about exoplanets. Right. And of course, to study exoplanets, right, and everything else out there in the universe, we need, as astronomers, to have pretty dark skies. We need to have dark skies for our telescopes. And dark skies don't just benefit astronomy, they actually have very large-reaching and pretty big effects on humans and on the environment around us, of which we are so much a part of. We are so much intertwined with the environment. So here to discuss some dark skies, some info about dark skies, is one of our educators, Sabrina Wilson. And let's send it over to her. Make sure to keep sending those questions into the chat, and she'll be standing by to answer those. And afterwards, we will be hearing, after Sabrina's talk, we'll be hearing from our director, Dr. Jeff Hall. So enjoy. And go ahead, Sabrina.
Howdy everyone, I'm Sabrina and I am a student at Northern Arizona University studying astrophysics and chemistry. I'm also an educator at Lowell Observatory. Melissa and Kathryn have painted a great picture as to just how unique our planet is and the vastness that is the universe. At night, our sky is painted with clusters of stars, other planets, nebulas, and much more. Unfortunately, many people across our globe do not get to see these objects in all their glory due to light pollution. But what is light pollution and what is its impacts besides keeping us from looking at the stars at night? Why do we care? Well, to be frank, light pollution is bad. Very bad. Specifically, light pollution is a brightening of the night sky caused by streetlights and other man-made light sources. For example, streetlights, car lights, most outdoor lighting in general. These light sources, if not properly shielded, pollute the night sky. If you've ever gone camping, you might have seen this halo along the sky's horizon. In small towns, you might have also experienced this. If you haven't experienced this or need a refresher, these images here are taken outside of cities in California, and you can see this ominous glow along the horizon in each one of them. So we have an idea of what light pollution looks like and in what forms it takes, but why exactly is light pollution bad? Besides not being able to see the stars at night, light pollution has a disruptive effect on our health, as well as the health of wildlife, energy, and astronomical research. This is a bit of a strange list though, right? How are all these things connected? So I'm going to go through a few of these really quickly so that connection is truly established. To get this rolling, let's start with human health. Light pollution brightens our night sky significantly, and this disrupts something known as our circadian rhythm. Our circadian rhythm is a 24-hour internal clock that runs in our brain. It's what makes you want to sleep at night and be awake and alert during the day. Your circadian rhythm tells your brain to release melatonin to help your body sleep, and is greatly impacted by light and darkness. So when it is lighter outside, our brain sends our body's signals to stay awake because we think it is earlier in the day. But disruption in this circadian rhythm doesn't just affect sleep patterns, but because it is run by the hypothalamus, It affects brainwave patterns, cell regulation, and other biological processes. Thus, disruption can lead to many health issues such as insomnia, depression, cancer, and cardiovascular disease. Extra light during the night also impairs our natural night vision, and thus glare from lights can truly harm our eyes. But as I mentioned earlier, the impacts of light pollution don't stop there. Here I have a ton of super cute animals. I have a little fox, some sea turtles, and cranes. Like humans, most organisms have a circadian rhythm. And just like us, the extra light at night impacts their natural schedule. When it is lighter at night, animals who migrate, such as these cute cranes, or forage for food or sleep, like the fox, have issues continuing on their natural behaviors, as they have to wait for the night to become darker and darker. Perhaps one of the saddest impacts of light pollution on wildlife is on the baby sea turtles. In a dark sky, a true natural setting, the sky appears lighter across the surface of the ocean. When baby sea turtles hatch, their instinct is to go towards the brightest part of the sky, which should be the ocean. However, due to light pollution of cities, the baby sea turtles crawl towards the town and often die. To keep this little sad fest going, light pollution wastes a lot of energy, and I mean a lot. Outdoor lighting that is mainly used to illuminate streets and parking lots in the US alone uses about 120 terawatt hours. Now, this is a very big number that might mean nothing to you, but it is enough to meet New York City's electricity needs for 2 whole years. The International Dark Sky Association, or IDA, estimates that 30% of outdoor lighting in the US is wasted, which may not sound like a whole lot, but that actually adds up to a whopping $3.3 billion and the release of 21 million tons of carbon dioxide a year. To offset that carbon emission, we would have to plant 875 million trees annually. And finally, the last impact of light pollution that I want to talk about is that of astronomical research. Our instruments are made to take in light to give us the best image of the sky. But if our telescope is gathering all that extra light that is not natural, our images become distorted. Here I have an image of the constellation of Orion. You can see his belt and his dagger, his little feetsies with Rigel, and his shoulders with Betelgeuse in both images. Now, the picture on the right is with a light pollution, and the one on the left is without. It is truly hard to get accurate data when the light pollution is skewing the images we are trying to interpret. The astronomy industry isn't just important in understanding our universe, but has contributed greatly to cell phone technology, X-ray, MRI, and other medical imaging, and satellite communications. So there you have it. Light pollution has many effects, ranging from our everyday lives to the exploration of the cosmos. I know I just hit you with a ton of sad statistics and facts, but I'm also here to tell you that there is hope. There are many actions and plans in place to help lessen light pollution, and Dr. Jeff Hall, the director of Lowell Observatory, is here to speak to you about them.
All right. Thank you, Sabrina, for that great introduction into just how important dark skies are, again, not just for astronomical research, but for humans, for the environment. It really, really is quite important. And to talk a little bit more about this, I have our director here, Dr. Jeff Hall, and true champion of dark skies. So take it away, Jeff.
Okay, thanks, Curtis, and thanks for emceeing the whole Earth Day event tonight. It's really been an interesting stream, and thanks also to our educators for the videos they put together for this. It's certainly true that we here at Lowell, we've been deeply involved in dark sky preservation. The sky is not only the source of all of our astronomical data, but it is a cultural resource for all of us. In fact, increasingly, the national monuments and parks are making efforts to establish themselves as dark sky preserves because the Park Service sees the nighttime sky as one of the resources that it considers part of its charge to preserve. You know, humans have been telling stories about the night sky ever since our earliest ancestors. And so preserving this connection that Sabrina talked about in all its forms, not just astronomy, but ecology and the environment and human health, and just our own enjoyment of the night sky is something we should all be involved with. So here in Flagstaff, we're very privileged because Flagstaff is the world's first international dark sky city. That is an official designation of the IDA, which Sabrina mentioned in her talk. And that was awarded to Flagstaff in 2001, and that represents a community commitment to preserving the quality of the night sky. So people often ask me, what can I do? And as viewers tonight, you may wonder, what can you do to help preserve dark skies? I'll touch on two things, and then I'll answer a question that's come in. The first point I'd like to make is that we are in a watershed moment right now for dark sky preservation, and that is because all over the world, communities are increasingly switching from legacy outdoor lighting systems such as high-pressure sodium, which are the sort of the round straw yellow fixtures you see on streetlights everywhere, to LED. Now, LEDs don't have to be bad for dark skies, but they certainly can. And the default kinds of LEDs that communities tend to install are the very, very bright white ones. And at a minimum, lumen per lumen, white LEDs will double the sky glow over a city relative to these older legacy systems. Now, there are ways to deal with that. And it's important that communities and city staff and city councils understand that. And so here in Flagstaff, we have been working for the past few years on a model solution that will use amber-colored LEDs that are much more dark sky friendly. These solutions are out there. We are hoping that once the Flagstaff solution is in place, we will be able to have materials that we can make available for others to consider and adopt. The other thing you can do is go to the website of the International Dark Sky Association and look at how you might help your community become a dark sky community. And the beauty of it is, and this was very smart of the IDA, you don't have to have a dark sky. One of their dark sky cities is Fountain Hills, Arizona, which is right on the edge of the Phoenix metro of 4 million people. It's not tied to the quality of the night sky, but to the individual community practices to preserve that. Now, at this point, I'll just put in a plug for our very next live stream. If you'd like to hear a lot more about this, because this is Earth Day and we're sort of celebrating all things about the Earth and the natural night sky, our next live stream will be at 9 a.m. Mountain Time, so noon Eastern. It's our 5th installment of our Cosmic Coffee series, and my guest will be Ruskin Hartley, who is the director of the International Dark Sky Association. And we're going to talk about all things dark skies and how to preserve dark skies and the IDA's mission and how you can help preserve the beauty of everything that's up there. So I'm going to, one question came in during the dark sky video from Nikita, saying, is it true that Elon Musk's 12,000 planned satellites around the Earth might affect astronomical researches in a bad way? The short answer to that question is yes. Fortunately, SpaceX has been very receptive and proactive to working with the astronomy community on this. I am the chair of the American Astronomical Society's Committee on Light Pollution, Radio Interference, and Space Debris, which, apart from being probably the longest title I have ever been privileged to have, it's been a very interesting time since the launch of the first Starlink satellites and the surprise at how bright they were. We have been working with SpaceX in a variety of ways over the past several months to look at ways that they might redesign their satellites to lower the brightnesses and solve this for astronomy. And in fact, Elon himself is on record saying that he intends the satellite system to have zero impact on astronomy, and we'll work to do that. Right now, I'm working with several colleagues to help convene a workshop at the end of June between members of the astronomical community and members of SpaceX, possibly other satellite operators, to try to understand what are the metrics and parameters we would have to hit to solve the problem and get that out in a white paper for everyone to react to. So it's certainly an interesting time. There are lots of uses of space. I think the vision of bringing broadband connectivity and communication to the world is a legitimate one. And what we have up there right now is a largely Wild West kind of frontier. And I think everybody is kind of moving along and trying to figure out how not to step on each other's toes. And it's been a very interesting process. Again, if you're interested in dark sky stuff, it should be a really interesting conversation tomorrow at 9 a.m. In the meantime, even in this era of quarantine and high stress, it's a little bit cathartic just to go out and look up at the marvels that you can see up there every night, right from your window and perfectly distant from everybody else. We want to help keep those magnificent sights accessible for everyone for decades to come. So with that, I'll pass it back to Curtis to wrap up and see if there are any final questions.
All right, thank you, Jeff. And just to piggyback off that last statement there, go outside, look up, and even though, say, those stars and planets are so far away, we are so very much connected. We are a part of the universe, a part of our solar system. And what better time to celebrate that than Earth Day? And Earth is truly humanity's home. It always will be, I think, no matter what. And I hope everybody around the world is enjoying Earth Day. I know here in Flagstaff we had a beautiful weather day, so I wish that on all of you out there. But Earth remains this pale blue dot. Again, harkening back just to that iconic image from 1980 from Voyager 1, over 4 billion miles away. Just goes to show that no matter where we go in life, I think we're always going to be looking back at where we came from, what's important to us, no matter what. So yeah, I want to thank everybody for joining us. It's been really fun here. This is exactly what I love to do, and with say our public viewing being closed lately, I'm really enjoying interacting with people again and answering questions. So thank you all for the great questions. It's been a blast. And we'll see you next time. So enjoy and have a great rest of your night, folks.
Bye.